Imagine floating in the deepest ocean you've ever conceived. But instead of water surrounding you, it's space itself. Vast, nearly empty space stretching in every direction for hundreds of millions of light years. You're not alone in this cosmic ocean. You're part of a small island, a collection of galaxies, including our own Milky Way, drifting through what scientists call a cosmic void. Tonight, we'll explore one of the most intriguing questions in modern cosmology: whether our entire local neighborhood of galaxies exists within one of the universe's largest empty regions. Hi, I'm Luna, and if you love falling asleep to curious science, quiet wonder, and starry night stories, you're in the right place. So grab your coziest blanket, get comfy, and don't forget to hit like and subscribe, because tonight, we're venturing into the cosmic deep, where emptiness tells a story as profound as any constellation, and where the spaces between galaxies hold secrets about the very structure of reality itself. The architecture of emptiness. To understand cosmic voids, we must first appreciate the grand architecture of the universe itself. Picture, if you can, the largest structures known to science. Not planets, not stars, not even galaxies, but the scaffolding upon which all these familiar objects hang like dewdrops on an invisible web. The universe, when viewed from the greatest distances, resembles something surprisingly familiar. A sponge, not the dense, colorful sponges we might use in our kitchens, but something far more ethereal, a three-dimensional foam where the solid parts are gossamer-thin filaments of galaxies, and the holes. The holes are voids so vast that light from one side takes longer to reach the other side than complex life has existed on Earth. These cosmic voids aren't simply regions where galaxies happen to be sparse. They represent a fundamental aspect of how matter organized itself in the early universe. In those first few 100 million years after the Big Bang, when the cosmos was still cooling from its initial fierce heat, tiny fluctuations in density, quantum whispers left over from inflation, began to grow under the influence of gravity. Where matter was slightly denser, it attracted more matter, growing into the filaments and nodes that would eventually become galaxy clusters and superclusters. But where matter was slightly less dense, it became increasingly empty as its meager contents were gravitationally pulled away toward those growing dense regions. Over billions of years, these underdense regions expanded and evolved into what we now call cosmic voids. The scale of these voids challenges our everyday intuition about space and distance. The largest known void, the giant void in the constellation Boötes, stretches approximately 330 million light-years across. To put this in perspective, if you could somehow shrink the Milky Way galaxy, with its 100 billion stars and diameter of 100,000 light-years, down to the size of a dinner plate, the giant void would still be larger than North America. Within such a void, galaxies are extraordinarily rare, where the cosmic average might contain several galaxies per cubic megaparsec, a unit of cosmic volume roughly equivalent to a cube 3.26 million light-years on each side. A typical void contains fewer than one-tenth that number. Some regions within the largest voids contain no observable galaxies at all across volumes that could comfortably hold thousands of Milky Way-sized galaxies. But voids aren't completely empty. Dark matter, that mysterious substance that outweighs normal matter by a ratio of 5 to 1, forms the gravitational scaffolding even in these seemingly barren regions. Computer simulations show that void regions contain sprawling, tenuous webs of dark matter, like cosmic spider silk, connecting the few galaxies that do exist in these regions. The boundaries of voids aren't sharp walls, but gradual transitions. As you move from the heart of a void toward its edge, galaxy density slowly increases until you reach the void's boundary, typically defined as where galaxy density reaches about 20% of the cosmic average. Beyond this boundary, density continues to increase as you approach the filaments and walls that form the cosmic web's denser regions. These transitions create some of the most beautiful structures in the universe, void walls and filaments, where galaxies are strung like pearls on cosmic strings of dark matter. Here, in these boundary regions, galaxy formation can be particularly active, as matter flowing out of the void interior collides with the denser material of the cosmic web. The local group's cosmic neighborhood now. Let us turn our attention closer to home, to the cosmic neighborhood that contains our Milky Way galaxy. We reside within what astronomers call the local group, a gravitationally bound collection of more than 80 galaxies dominated by three large spiral galaxies, our own Milky Way, the Andromeda Galaxy, and the somewhat smaller Triangulum Galaxy. The local group spans approximately 10 million light-years across, a vast distance by terrestrial standards, yet barely a speck when compared to the cosmic web's largest structures. This collection of galaxies moves through space as a cohesive unit, bound together by gravity and slowly converging. In roughly 4.5 billion years, the Milky Way and Andromeda will merge in a cosmic dance that will reshape both galaxies, creating a new elliptical galaxy that astronomers have playfully named Milkomeda. But the local group doesn't exist in isolation. It's part of a much larger structure called the local supercluster, or the Virgo supercluster, which contains thousands of galaxies organized into dozens of galaxy groups and clusters. At the heart of this supercluster lies the Virgo cluster, a dense concentration containing over 1,300 galaxies that exerts a gravitational influence extending across the entire supercluster. Recent discoveries have revealed that even the local supercluster is just one part of an even more massive structure, the Laniakea supercluster. This cosmic continent contains over 100,000 galaxies and spans 520 million light-years. Its name means immeasurable heaven in Hawaiian, a fitting description for a structure so vast that light takes 500 million years to cross from one side to the other. The motion of galaxies within Laniakea reveals the presence of what astronomers call the Great Attractor, a gravitational anomaly that appears to be drawing much of our local universe toward it. This attractor lies hidden behind the plane of our own galaxy, obscured by the dust and stars of the Milky Way, making it one of the most mysterious large-scale features in our cosmic neighborhood. But here's where our story takes an intriguing turn. As astronomers have mapped the distribution of galaxies around us with increasing precision, they've discovered something unexpected about our cosmic location. When they look at galaxy counts in different directions from Earth, they don't see the uniform distribution one might expect from a typical cosmic location. Instead, they see evidence that we may be living in a region of space that's notably underdense compared to the cosmic average. This isn't immediately obvious because we're still surrounded by thousands of galaxies within a few 100 million light-years. But when astronomers compare our local galaxy density to what they observe in other parts of the universe, a pattern emerges suggesting that our entire local supercluster might be situated within or near the edge of a cosmic void. This possibility has profound implications for our understanding of cosmic history and our place within it. If the Milky Way indeed resides in a void, it would help explain several puzzling observations about our cosmic neighborhood, from the peculiar motions of nearby galaxies to the apparent acceleration of the universe's expansion, a phenomenon we attribute to dark energy, the KBC void. Our cosmic address, the most compelling evidence for our void-dwelling existence, comes from the work of astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who in 2013 published research describing what they called the KBC void, named after their initials. This structure, if it exists as they propose, would be one of the largest known voids in the universe, with our local group positioned not at its center, but roughly 2/3 of the way toward its edge. The KBC void, according to their analysis, spans approximately 2 billion light-years across and contains significantly fewer galaxies than would be expected for a typical region of space this size. The evidence for this void comes from careful galaxy surveys that count the number of galaxies at different distances from the Milky Way. Comparing these counts to what would be expected in an average cosmic location. When astronomers plot galaxy density as a function of distance from our position, they see a consistent underdensity extending out to roughly 1 billion light-years in most directions. This underdensity isn't dramatic. Galaxies are perhaps 20–30% less common than the cosmic average, but it's persistent and statistically significant across multiple independent surveys. The KBC void's existence would help resolve what astronomers call the Hubble tension, a puzzling discrepancy in measurements of the universe's expansion rate. When astronomers measure the expansion rate using nearby supernovae, they get one value. When they measure it using the cosmic microwave background, light left over from the Big Bang, they get a slightly different value. This difference might seem small, but it's large enough to suggest either measurement errors or new physics. If we live in a void, the resolution becomes elegantly simple. The expansion rate measurements using nearby supernovae would be systematically biased because they're sampling galaxies in an underdense region where space expands differently than the cosmic average. The cosmic microwave background, representing the universe as a whole, would give the true cosmic expansion rate. This void hypothesis also explains another puzzling observation: the apparent smoothness of the cosmic microwave background in our local sky. If we lived in a typical cosmic location, we might expect to see more variation in this ancient light due to the gravitational effects of nearby massive structures. But if we're in a relatively empty region, the cosmic microwave background would appear smoother, exactly what we observe. The boundaries of the KBC void, like all cosmic voids, aren't sharp transitions, but gradual changes in galaxy density. As you move outward from our local position toward the void's edge, galaxy density slowly increases. At roughly 1 billion light-years from the Milky Way, the density begins to approach cosmic average values, marking the transition from void interior to void wall. These void walls contain some of the most spectacular galaxy clusters in our observable universe. The Coma cluster, the Perseus cluster, and the Great Shapley supercluster all lie roughly at the distances where we would expect to find the KBC void's boundaries. These dense concentrations of galaxies represent the material that was gravitationally stripped from the void's interior over billions of years of cosmic evolution. But the KBC void hypothesis remains controversial within the astronomical community. Some researchers argue that the apparent underdensity around us could be explained by systematic errors in galaxy surveys or by the peculiar motions of galaxy clusters. Others suggest that what appears to be a void might simply be a statistical fluctuation, a randomly underdense region that happens to contain our galaxy, but doesn't represent a true cosmic void. The debate continues as new galaxy surveys with improved precision map our cosmic neighborhood with ever greater accuracy. Each new dataset brings us closer to definitively answering whether we truly live in one of the universe's great empty spaces, or whether our cosmic address is more typical than these observations suggest. To truly understand cosmic voids and their significance, we must delve into the physics that governs these vast empty regions. Voids aren't static features of the universe, but dynamic systems that evolve according to the laws of gravity, thermodynamics, and cosmology. In the early universe, roughly 400,000 years after the Big Bang, matter and radiation decoupled for the first time. Before this moment, known as recombination, the universe was opaque. Photons couldn't travel far before interacting with free electrons and protons. But as the universe cooled, electrons and protons combined to form neutral hydrogen atoms, making space transparent for the first time. At this moment, tiny density fluctuations that had been frozen in place by radiation pressure were suddenly free to grow under gravity's influence. These fluctuations, originally quantum mechanical in nature, and inflated to cosmic scales during the universe's brief inflationary period, became the seeds of all large-scale structure. In regions where matter density was slightly higher than average, gravity began pulling in additional matter from the surrounding space. Over millions of years, these overdense regions grew into the first dark matter halos, which eventually became the sites of the first star formation and galaxy assembly. But in regions where matter density was slightly lower than average, the opposite process occurred. What little matter existed in these regions was gradually pulled away by the stronger gravitational attraction of nearby overdense areas. Over hundreds of millions of years, these underdense regions became increasingly empty, evolving into the cosmic voids we observe today. This process, known as gravitational instability, operates according to well-understood physics, but its outcomes are remarkably complex. Computer simulations of structure formation show that void evolution is intimately connected to the growth of cosmic web filaments and galaxy clusters. As matter flows out of underdense regions toward overdense ones, it creates the intricate network of sheets, filaments, and nodes that characterizes the universe's largest structures. Within void interiors, the physics becomes particularly interesting. The low matter density means that gravity's influence is weak, allowing other forces to play larger roles than they do in denser cosmic regions. Gas pressure, magnetic fields, and even the subtle effects of dark energy become more important in determining the behavior of the sparse matter that remains. The few galaxies that do form within void interiors often have unusual properties. They tend to be smaller, bluer, and more actively forming stars than galaxies in typical cosmic environments. This occurs because void galaxies experience fewer gravitational encounters with neighbors, allowing them to retain more of their original gas supplies for ongoing star formation. Void galaxies also move differently than their counterparts in denser regions. While galaxies in clusters and filaments are subject to complex gravitational interactions that can fling them about at high speeds, void galaxies typically move more slowly and in more predictable patterns. Their motions are dominated by the large-scale expansion of the universe itself, rather than local gravitational perturbations. The expansion of voids follows the same cosmological laws that govern universal expansion, but with some important differences. Because voids contain less matter than average cosmic regions, they experience less gravitational deceleration. This means that void regions expand slightly faster than the universe as a whole, a phenomenon that may contribute to the apparent acceleration of cosmic expansion that we attribute to dark energy. Recent theoretical work suggests that the interplay between void expansion and dark energy may be more complex than previously thought. Some models propose that the apparent acceleration of universal expansion could be partially explained by our location within a void, where local expansion rates exceed the cosmic average. This possibility remains highly speculative, but represents an active area of cosmological research. The magnetic fields within voids also behave differently than in denser cosmic regions. While galaxy clusters and filaments can contain strong magnetic fields generated by turbulent gas motions and stellar processes, void regions typically have much weaker fields. However, these weak magnetic fields can extend over vast distances, creating some of the largest coherent magnetic structures in the universe. Temperature profiles within voids reveal another aspect of their unique physics. The sparse gas in void interiors is typically cooler than gas in denser regions because it experiences less gravitational heating and fewer shock waves from galaxy interactions. This cool gas can be difficult to detect with current instruments, making it challenging to study the detailed physics of void interiors. As our understanding of void physics continues to evolve, astronomers are developing new techniques to probe these seemingly empty regions. Radio telescopes sensitive to the 21-centimeter emission line of neutral hydrogen may soon allow us to map the distribution of gas within voids, revealing the detailed structure of the cosmic web's most tenuous components. The question of whether we live in a cosmic void requires careful analysis of observational evidence from multiple independent sources. Astronomers have developed several different approaches to test this hypothesis, each with its own strengths and limitations. The most direct approach involves counting galaxies at different distances from the Milky Way and comparing these counts to theoretical expectations for a typical cosmic location. This sounds straightforward, but it requires careful consideration of selection effects, measurement uncertainties, and systematic biases that can affect galaxy surveys. Early evidence for local underdensity came from studies of Type Ia supernovae stellar explosions that serve as standard candles for measuring cosmic distances. These supernovae provided the first evidence for the acceleration of cosmic expansion, leading to the discovery of dark energy. But some astronomers noticed that the distribution of nearby supernovae seemed unusually sparse compared to what might be expected. More recent analyses have used large galaxy redshift surveys to map the three-dimensional distribution of galaxies around us. The 2-degree field galaxy redshift survey, the Sloan Digital Sky Survey, and more recent projects have cataloged millions of galaxies, providing unprecedented detail about local cosmic structure. When astronomers analyze these surveys, they consistently find evidence for underdensity, extending out to distances of several 100 million light-years. The underdensity isn't extreme, typically 20–40% below cosmic average, but it's persistent across different survey techniques and statistical methods. One particularly compelling line of evidence comes from studies of the local Hubble flow, the expansion of space in our immediate cosmic neighborhood. If we lived in a typical cosmic location, this expansion should proceed smoothly according to Hubble's law, which relates recession velocity to distance. But observations reveal systematic deviations from this smooth expansion, with some nearby galaxies moving more slowly than expected and others more quickly. These peculiar motions can be explained if we live in an underdense region where the gravitational influence of distant massive structures creates bulk flows in our local space. Computer simulations of structure formation predict exactly these types of motions for galaxies located within or near cosmic voids. Another line of evidence comes from studies of the cosmic microwave background radiation. This ancient light, emitted when the universe was only 380,000 years old, carries information about the distribution of matter and energy at that early epoch. If we live in a void, it should create a subtle signature in the microwave background, called the integrated Sachs-Wolf effect. This effect occurs when microwave background photons travel through regions of changing gravitational potential. As photons pass through an expanding void, they gain energy when entering the void's gravitational well and lose energy when exiting it. But because the void expands during the photon's transit time, the energy loss is slightly less than the energy gain, creating a net temperature increase in the microwave background. Several research groups have reported detections of this effect in the direction of known void regions, though the signals are subtle and remain somewhat controversial. If confirmed, these observations would provide independent evidence that large cosmic voids do indeed affect the propagation of light across cosmic distances. The study of gravitational lensing provides yet another approach to testing the void hypothesis. Massive structures in the universe bend the paths of light rays, creating distortions in the images of background galaxies. If we live in a void, there should be fewer massive structures along our line of sight to distant galaxies, resulting in less gravitational lensing than would be expected from a typical cosmic location. Preliminary studies of weak gravitational lensing in our local universe do suggest somewhat less lensing distortion than theoretical models predict, though this field remains technically challenging, and the results are not yet definitive. Perhaps the most intriguing observational test involves measuring the fine structure constant, a fundamental parameter of physics that determines the strength of electromagnetic interactions. Some theoretical models predict that this constant might actually vary slightly across different regions of the universe, with voids having slightly different values than denser regions. Spectroscopic observations of distant quasars can measure the fine structure constant with extraordinary precision by analyzing the absorption lines created when quasar light passes through intervening gas clouds. Several research groups have reported evidence for spatial variations in this constant, though the effects are extremely small and remain controversial within the physics community. The cumulative weight of observational evidence suggests that we do indeed live in an underdense region of the universe, though the magnitude and extent of this underdensity remain subjects of active research. Future galaxy surveys, including the upcoming Euclid space mission and the Large Synoptic Survey Telescope, will provide much more precise measurements of local cosmic structure. These new observations should definitively answer whether the Milky Way resides in a cosmic void, or whether the apparent underdensity around us can be explained by other factors. The answer will have profound implications for our understanding of cosmic structure formation, dark energy, and our place in the universe. Implications for cosmology and dark energy. If we do indeed live within a cosmic void, this discovery would have far-reaching implications for our understanding of cosmology and the mysterious force known as dark energy. The story of dark energy begins with one of the most surprising discoveries in 20th century astronomy: the accelerating expansion of the universe. In 1998, two independent teams of astronomers studying distant Type Ia supernovae made an unexpected discovery. These stellar explosions, which serve as cosmic lighthouses due to their consistent brightness, revealed that the expansion of the universe is not slowing down as most scientists expected, but is instead speeding up. This acceleration implies the existence of a repulsive force pervading all of space, what cosmologists call dark energy. Dark energy is thought to comprise roughly 68% of the universe's total energy density, making it the dominant component of cosmic evolution. Yet despite decades of intensive research, its fundamental nature remains one of the greatest mysteries in physics. The leading theoretical candidate is the cosmological constant, a constant energy density inherent to space itself. But this explanation raises its own profound puzzles. The void hypothesis offers a potentially simpler explanation for some of the observations attributed to dark energy. If we live in an underdense region of the universe, our local measurements of cosmic expansion would be systematically biased compared to the true cosmic average. Void regions expand faster than the universe as a whole because they contain less matter to gravitationally decelerate the expansion. This local acceleration could mimic the signatures of dark energy in nearby supernova observations, while the cosmic microwave background, which samples the universe as a whole, would reflect the true cosmic expansion rate. The apparent discrepancy between these different measurements, known as the Hubble tension, might thus be resolved without invoking exotic new physics. However, this explanation faces significant challenges. Detailed calculations suggest that the KBC void, even if it exists as proposed, would not be large enough or underdense enough to fully account for the observed acceleration. The void would need to be substantially larger, perhaps 5-10 billion light-years across, to completely eliminate the need for dark energy. Moreover, other observations of cosmic acceleration, including studies of the cosmic microwave background and large-scale structure formation, appear to require dark energy even if local measurements are affected by void residence. The void hypothesis might reduce the amount of dark energy needed to explain observations, but it probably cannot eliminate the need for it entirely. Nevertheless, the possibility that our cosmic location affects our interpretation of universal expansion has important implications for cosmological measurements. If confirmed, it would require astronomers to carefully account for local environmental effects when using nearby observations to infer global cosmic properties. The void hypothesis also affects our understanding of cosmic structure formation. If the Milky Way formed within a void environment, it would have experienced a different evolutionary history than galaxies in typical cosmic locations. Void galaxies typically form later, grow more slowly, and experience fewer major mergers than galaxies in denser environments. This could help explain some puzzling aspects of our galaxy's structure and history. The Milky Way appears to have had a relatively quiet merger history compared to many similar galaxies, with its last major merger occurring over 10 billion years ago. If we live in a void, this quiescent history would be more typical of our environment. The void hypothesis might also affect our estimates of the universe's matter density. Current cosmological models are calibrated using observations that assume we live in a typical cosmic location. If we actually reside in an underdense region, these models might systematically underestimate the true cosmic matter density. Such systematic errors could have cascading effects on our understanding of cosmic evolution, from the formation of the first stars and galaxies to the ultimate fate of the universe. They might also affect our interpretation of observations related to cosmic inflation, the physics of the early universe, and the nature of dark matter. The implications extend beyond cosmology to fundamental physics. Some theories attempt to explain dark energy through modifications to Einstein's general theory of relativity on cosmic scales. If local environmental effects can partially account for apparent cosmic acceleration, it might provide clues about which modified gravity theories are most promising. Conversely, if detailed studies confirm that we live in a typical cosmic environment despite apparent local underdensity, it would strengthen the case for dark energy as a fundamental property of spacetime, rather than an environmental effect. The quest to understand our cosmic location thus represents more than academic curiosity. It touches on some of the deepest questions in physics and astronomy. Are we typical observers in a typical cosmic location? Or do we occupy a special place that affects our view of the universe? The answer will help determine whether the apparent acceleration of cosmic expansion reflects new fundamental physics, or simply the biased perspective of void-dwelling observers. To fully appreciate the significance of potentially living in a cosmic void, we must understand these empty regions within the broader context of the cosmic web, the largest scale structure of the universe. This web represents the ultimate outcome of billions of years of gravitational evolution, starting from tiny quantum fluctuations in the very early universe. Imagine the cosmic web as a three-dimensional spider's web of unimaginable size, where the silken strands are replaced by chains of galaxies and dark matter, and the spaces between strands are vast voids. But unlike a spider's web, which maintains its structure through material strength, the cosmic web is held together and shaped entirely by gravity acting over cosmic time. The web's architecture reveals itself when astronomers map the positions of millions of galaxies across vast volumes of space. What emerges is a pattern of stunning regularity. Galaxies are organized into sheets, filaments, and nodes, with the densest concentrations occurring where multiple filaments intersect. These intersection points become galaxy clusters, some of the most massive gravitationally bound structures in the universe. Between these dense regions stretch the cosmic voids, occupying roughly 80% of the universe's volume despite containing less than 20% of its matter. These voids aren't completely empty, but are rather regions where the density of normal matter and dark matter falls significantly below the cosmic average. They represent the photographic negative of cosmic structure, spaces that reveal themselves through absence rather than presence. The cosmic web's formation began in earnest roughly 13.5 billion years ago, when the universe had cooled sufficiently for matter to begin collapsing under its own gravity. Initially, the distribution of matter was nearly uniform, with only tiny variations in density, fluctuations so small they amounted to only 1 part in 100,000. But these minuscule variations contain the seeds of everything we see today. Regions with slightly higher density attracted additional matter through gravitational attraction, growing slowly but inexorably over millions of years. Meanwhile, regions with lower density saw their sparse matter gradually drawn away toward these growing concentrations. Dark matter played a crucial role in this process. Because dark matter interacts only gravitationally, it could begin collapsing immediately after matter and radiation decoupled. Normal matter, still coupled to radiation through electromagnetic interactions, had to wait until the universe cooled further before it could fall into the gravitational wells that dark matter had already begun to excavate. As structure formation progressed, the universe developed a hierarchical pattern of organization. Small dark matter halos formed first, then merged to create larger halos, which in turn combined to form galaxy groups, clusters, and eventually superclusters. This bottom-up assembly process naturally created the web-like pattern we observe today. The cosmic web's geometry reflects the universe's underlying physics in profound ways. The sheet-like structures called walls form when matter collapses primarily in one direction, creating vast, thin layers of galaxies. Filaments develop when matter collapses in two directions, creating cosmic strings of dark matter and galaxies. Nodes occur where matter collapses in all three spatial dimensions, forming the universe's densest regions. Voids emerge naturally from this same process. They represent regions where the initial density was low enough that matter collapse never began in earnest. Instead of growing denser over time, these regions became increasingly empty as their sparse contents were gravitationally stripped away by surrounding overdense areas. The cosmic web exhibits a remarkable property called scale invariance over certain distance ranges. This means that if you zoom in or out by factors of 10 or even 100, the same basic patterns of structure repeat themselves. Superclusters contain clusters, which contain groups, which contain galaxies, which contain star clusters, each level showing similar patterns of dense nodes connected by filamentary structures. However, this scale invariance breaks down at very large scales, larger than about 100 million light-years, where the universe appears increasingly smooth and homogeneous. This transition from structured to smooth represents one of the fundamental features of our cosmos and provides crucial constraints on theories of cosmic evolution. The cosmic web is not static, but continues to evolve as the universe ages. Computer simulations predict that over the next 100 billion years, continued cosmic expansion and the accelerating influence of dark energy will gradually stretch and dilute the web's structures. Eventually, most galaxies will become increasingly isolated as the expansion of space overwhelms their gravitational bonds. But for now, we live during a golden age of cosmic structure, when the web has had time to develop its intricate architecture, but hasn't yet been torn apart by cosmic expansion. If we do indeed reside within one of the web's great voids, we occupy a unique vantage point for observing this magnificent structure. Surrounded by emptiness, yet connected to the cosmic community through gravity's invisible threads, our potential void residence would make us somewhat unusual among intelligent observers in the universe. Most galaxies, and presumably most life, exist within the web's denser regions, where galaxy interactions and active star formation create the complex chemical environments needed for biology. Void galaxies, while not impossibly rare, represent a minority population in cosmic demographics. This raises intriguing questions about the relationship between cosmic environment and the development of complexity. Did our residence in a relatively quiet void contribute to the stable, long-term conditions that allowed complex life to evolve on Earth? Or are we simply among the fortunate minority of observers who happen to live in one of the universe's great empty spaces? Living in a cosmic void, if that's indeed where we find ourselves, would place the Milky Way in what we might call the cosmic suburbs, not in the bustling downtown regions where galaxies cluster densely together, nor in the complete rural isolation of a void's deepest interior, but somewhere in between. This suburban cosmic address would have profound implications for the history and future of our galaxy, and perhaps for the development of life itself. The cosmic suburbs are quieter places than the dense galaxy clusters that form the universe's urban centers. In these crowded regions, galaxies regularly encounter one another, triggering spectacular bursts of star formation, feeding supermassive black holes, and sometimes merging in cosmic collisions that reshape both participants. The intergalactic medium in these regions is hot and turbulent, ionized by the intense radiation from active galactic nuclei, and heated by shock waves from galactic interactions. By contrast, galaxies in void environments experience a more peaceful existence. They interact less frequently with neighbors, allowing them to evolve in relative isolation. Their gas supplies remain cooler and less disturbed, enabling steady, prolonged periods of star formation, rather than the violent bursts common in denser environments. This quieter lifestyle appears to characterize the Milky Way's history. Our galaxy shows evidence of ancient merger events, including the dramatic collision that created the galactic halo and the more recent disruption of the Sagittarius dwarf galaxy. But compared to many galaxies of similar mass, the Milky Way has experienced relatively few major disturbances in the past several billion years. The most significant upcoming event in our galaxy's future is the planned collision with the Andromeda Galaxy, predicted to occur in approximately 4.5 billion years. But even this event, dramatic as it will be, represents the kind of major merger that galaxies in denser environments might experience multiple times throughout their histories. Our suburban cosmic location may have been crucial for the development of life on Earth. Planet formation appears to require specific conditions: a stable stellar environment, sufficient heavy elements created by previous generations of stars, and protection from the intense radiation that pervades denser cosmic regions. Void environments provide several advantages for astrobiology. The lower density of galaxies means fewer nearby supernovae, gamma-ray bursts, and other high-energy phenomena that could sterilize planetary surfaces across large regions of space. The reduced tidal forces from neighboring galaxies allow stellar orbits within galaxies to remain more stable over cosmic time scales. The chemical evolution of void galaxies also follows a different trajectory than galaxies in denser environments. Because they experience fewer merger events, they tend to form stars more gradually and steadily. This allows for a more uniform distribution of heavy elements, the carbon, oxygen, silicon, and iron, that form the building blocks of rocky planets and biological molecules. However, void residence isn't necessarily optimal for life. The reduced rate of galaxy interactions means less efficient triggering of star formation, potentially leading to fewer opportunities for planet formation. The lower density of nearby galaxies also means that any technological civilizations that develop would face much greater challenges in eventually expanding beyond their home galaxy. The nearest large galaxy to the Milky Way, Andromeda, lies roughly 2.5 million light-years away, a distance that represents an almost insurmountable barrier for interstellar travel, even for highly advanced civilizations. In denser cosmic regions, galaxies are often separated by much smaller distances, potentially making intergalactic expansion more feasible. From an observational perspective, our void residence provides both advantages and limitations for astronomy. The reduced density of nearby galaxies means less confusion when observing distant objects, allowing clearer views of the distant universe. The cosmic microwave background appears smoother from our location, providing cleaner data about the early universe. But the same emptiness that provides clear views also means fewer nearby targets for detailed study. Astronomers must look farther to find examples of exotic galactic phenomena, and the reduced number of nearby galaxies limits our ability to study galactic evolution through statistical comparisons. The psychological and philosophical implications of void residence are perhaps equally profound. Humans have always sought to understand their place in the cosmos, and the discovery that we might live in one of the universe's great empty spaces adds a new dimension to this ancient quest. Are we cosmically isolated, dwelling in a sparse region that separates us from the universe's main centers of activity? Or are we fortunate residents of a peaceful cosmic suburb, protected from the violence and chaos that characterize denser regions while still connected to the larger cosmic community? The answer may depend on perspective. From the viewpoint of galactic astronomy, voids might seem like cosmic backwaters, underdeveloped regions that missed out on the main action of cosmic evolution. But from the perspective of astrobiology, these same regions might represent oases of stability in an otherwise turbulent universe. Our void residence, if confirmed, would make Earth and humanity somewhat special, not in the sense of occupying the center of the universe, as pre-Copernican astronomers believed, but in the sense of existing in an unusual cosmic environment that may have been particularly conducive to the development of complex life. This specialness would be statistical rather than fundamental. There's nothing physically unique about void regions that makes them fundamentally different from other parts of the universe, but their particular combination of properties, isolation, stability, and clarity, may have created conditions particularly favorable for the emergence and persistence of complex life. As we drift deeper into our exploration of cosmic emptiness, it's worth considering how our understanding of voids will evolve in the coming decades. The field of void cosmology stands at an exciting threshold, with new observational capabilities and theoretical developments promising to revolutionize our knowledge of these vast, empty regions. The next generation of astronomical surveys will map cosmic structure with unprecedented precision and completeness. The European Space Agency's Euclid mission, launched in 2023, is designed to survey billions of galaxies across more than a third of the sky. Its measurements will provide the most detailed three-dimensional map of cosmic structure ever created, including precise characterization of void properties across cosmic time. Similarly, the Vera C. Rubin Observatory in Chile will conduct the legacy survey of space and time, photographing the entire visible southern sky every few nights for 10 years. This survey will discover and catalog tens of billions of galaxies, providing statistical power to detect even subtle void signatures and trace their evolution over cosmic history. These surveys will allow astronomers to address fundamental questions about void formation and evolution. Did voids grow primarily through the expulsion of matter toward denser regions? Or did they form through the preferential expansion of initially underdense areas? How do void properties depend on cosmological parameters like dark matter density and dark energy equation of state? The surveys will also enable precise tests of the void hypothesis for our local cosmic environment. By mapping galaxy distributions with exquisite detail, astronomers will definitively determine whether the Milky Way resides in a cosmic void, or whether apparent local underdensity results from statistical fluctuations or systematic measurement errors. Advanced computer simulations will complement these observational advances. The next generation of cosmological simulations will model the formation and evolution of cosmic structure from the Big Bang to the present, with unprecedented resolution and physical realism. These simulations will predict the detailed properties of voids, including their internal structure, boundary dynamics, and effects on cosmic observables. Machine learning and artificial intelligence techniques are already beginning to transform void research. These computational tools can identify subtle patterns in galaxy distributions that might escape human recognition, potentially revealing new types of cosmic structures or unexpected correlations between void properties and cosmic evolution. The study of voids will also benefit from advances in theoretical cosmology. Modified gravity theories, which attempt to explain cosmic acceleration without invoking dark energy, make specific predictions about void properties and evolution. Detailed observations of void characteristics will thus provide crucial tests of these alternative theories. Perhaps most intriguingly, voids may serve as laboratories for studying dark energy itself. The accelerated expansion that characterizes dark energy should manifest differently in void regions compared to denser cosmic areas. By comparing expansion rates in voids versus filaments, astronomers may gain new insights into dark energy's fundamental nature. The possibility of using voids to probe dark energy has sparked interest in developing new observational techniques. Radio astronomers are working to detect the faint 21-centimeter emission from neutral hydrogen gas in void regions, which would provide direct measurements of void expansion rates. Similarly, gravitational wave observatories may eventually detect signals from merging black holes in void regions, offering another probe of expansion dynamics. Void research will also intersect with the search for extraterrestrial intelligence. If technological civilizations are more likely to develop in the stable environments of void regions, then surveys for technosignatures might be most productive when focused on void galaxies rather than galaxies in denser cosmic environments. The implications extend to astrobiology more broadly. As our understanding of void environments improves, astrobiologists will be better positioned to assess whether these regions truly provide advantages for life's emergence and evolution, or whether the apparent correlation between void residence and biological development reflects selection effects rather than causation. Looking further into the future, void research may contribute to humanity's long-term cosmic perspective. If we do live in a void, our descendants will eventually need to grapple with the implications of cosmic isolation as the universe continues to expand. Understanding void dynamics will be crucial for predicting how cosmic expansion affects the accessibility of neighboring galaxies and the ultimate fate of matter and energy in our cosmic neighborhood. The study of cosmic voids thus represents far more than an academic exercise in mapping empty space. These seemingly barren regions encode fundamental information about cosmic evolution, dark energy, and our place in the universe. As observational and theoretical capabilities continue to advance, voids will likely play an increasingly central role in our understanding of cosmology. As we near the end of our journey through cosmic emptiness, it's natural to reflect on the deeper implications of what we've discovered. The possibility that we live in a cosmic void touches on fundamental questions that have puzzled humans throughout history. What is our place in the universe? Are we typical or special? How does our cosmic environment shape our understanding of reality itself? The concept of living in emptiness might initially seem unsettling. After all, humans are social creatures who find comfort in community and connection. The idea that our entire galaxy exists in a cosmic suburb, separated from the universe's main centers of activity by vast distances, could evoke feelings of isolation or cosmic loneliness. But perhaps this perspective reflects our terrestrial biases more than cosmic reality. From a galactic viewpoint, the Milky Way is far from isolated. We're surrounded by dozens of companion galaxies in the local group, connected to thousands more galaxies in the local supercluster, and gravitationally influenced by massive structures extending across hundreds of millions of light years. Even if we do live in a void, we remain intimately connected to the broader cosmic web through the fundamental forces of physics. Gravity links us to distant galaxy clusters. Electromagnetic radiation carries information from across the observable universe, and the quantum vacuum connects us to the deepest levels of physical reality. The void hypothesis also raises profound questions about cosmic democracy. Are we typical observers in a typical cosmic location, or do we represent a statistical minority dwelling in unusual circumstances? This question touches on one of the most important principles in modern science, the Copernican principle, which assumes that we don't occupy a special or privileged position in the universe. The Copernican principle has guided scientific thinking for centuries, leading to the recognition that Earth orbits the Sun rather than standing at the center of the universe, that the Sun is an ordinary star among billions in our galaxy, and that the Milky Way is just one galaxy among trillions in the observable universe. If we live in a cosmic void, it wouldn't violate the Copernican principle in its original sense. We still wouldn't occupy the center of the universe or hold any fundamentally privileged position, but it would suggest that our local cosmic environment is somewhat atypical, which could affect our interpretation of cosmic observations and our understanding of universal properties. This possibility highlights the importance of environmental context in scientific observation. Just as terrestrial astronomers must account for atmospheric effects when observing distant stars, cosmologists may need to account for void effects when inferring universal properties from local measurements. The implications extend to our understanding of cosmic history and future. If void residents contributed to the stable conditions that allowed complex life to evolve on Earth, it suggests that biological development may be influenced by cosmic environment in ways we're only beginning to appreciate. This doesn't imply that life requires void environments. The universe contains billions of galaxies in diverse cosmic settings, many of which likely harbor living worlds. But it does suggest that the relationship between cosmic structure and biological evolution may be more nuanced than previously thought. Looking toward the future, void residents would shape humanity's long-term cosmic prospects. The accelerating expansion of the universe, driven by dark energy, will eventually carry distant galaxies beyond our observable horizon. Galaxies in void regions will become isolated more quickly than those in denser cosmic areas. In the far future, trillions of years from now, observers in void galaxies might find themselves truly alone, unable to see evidence of the broader universe beyond their local group. They would inhabit what cosmologists call island universes, isolated by expansion and surrounded by empty space, expanding faster than light can cross it. But this cosmic loneliness lies so far in the future that it has little relevance to current human concerns. For the foreseeable future, we remain connected to a rich and vibrant universe, filled with galaxies, stars, and potentially countless other worlds harboring life and intelligence. The study of cosmic voids also offers lessons about the value of apparent emptiness. In human affairs, we often focus on fullness, density, and activity, while overlooking the importance of space, silence, and stillness. Voids remind us that emptiness can be as significant as matter, that the spaces between objects can be as important as the objects themselves. In cosmic structure formation, voids play crucial roles despite their apparent emptiness. They provide the low-pressure regions that allow matter to flow toward denser areas. They serve as cosmic laboratories where different physical processes dominate, and they offer unique perspectives on cosmic evolution and fundamental physics. Similarly, in human experience, periods of quiet contemplation, open spaces in our schedules, and moments of stillness often prove as valuable as times of intense activity. The cosmic void hypothesis, whether ultimately confirmed or refuted, reminds us that emptiness and fullness are complementary aspects of reality rather than opposing forces. Gentle conclusions under starlit skies, as our exploration of cosmic voids draws to a peaceful close. Let us step outside for a moment, away from the technical details and complex theories, to simply look up at the night sky. There, scattered across the darkness like luminous dust, are the stars of our galaxy, each one a sun, many possibly warming worlds of their own. If you find yourself in a place with dark skies, away from city lights, you might glimpse the faint, cloudy band of the Milky Way stretching overhead. This ethereal glow represents our edge-on view of our galaxy's disk, containing hundreds of billions of stars extending across 100,000 light-years of space. Yet even this vast collection of suns and worlds might occupy just a tiny corner of an even vaster emptiness. The possibility that we live in a cosmic void adds a new dimension to the ancient human practice of stargazing. When we look up at the night sky, we might be looking out from within one of the universe's great empty spaces, a cosmic clearing in the forest of galaxies, a quiet harbor in the ocean of space-time. This perspective transforms our understanding of cosmic solitude. Rather than being adrift in an uncaring void, we might be nestled in a peaceful cosmic valley, protected from the turbulent interactions that characterize denser regions of the universe. Our apparent isolation becomes a form of sanctuary, a stable environment that has allowed complexity and consciousness to emerge over billions of years. The stars we see overhead tell stories of cosmic chemistry and stellar evolution that span billions of years. Each photon of starlight that reaches our eyes has traveled vast distances, carrying information about nuclear processes in stellar cores, the formation of heavy elements, and the dynamics of galactic rotation. Even if we live in a void, we remain connected to the broader universe through these messengers of light. Consider the remarkable journey that brought us to this moment of contemplation. The atoms in our bodies were forged in the hearts of ancient stars and dispersed by stellar explosions across cosmic time. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created through stellar nucleosynthesis and stellar death, then incorporated into the molecular clouds that eventually gave birth to our solar system. If we do live in a cosmic void, this stellar alchemy still connects us to the broader universe. The heavy elements that make life possible were created in stars throughout the cosmic web, then mixed and redistributed through galactic winds, supernova explosions, and the gradual drift of matter across cosmic time. Our void residence, should it prove real, doesn't diminish our cosmic heritage. It simply adds another chapter to the story of how matter and energy have moved and evolved across billions of years to create the conditions for our existence. The gentle expansion of space itself, whether accelerated by dark energy or enhanced by our location in an underdense region, continues around us even as we sleep. This cosmic breathing, so slow and vast that it's imperceptible on human timescales, represents one of the most fundamental aspects of our universe, the legacy of the Big Bang still playing out across cosmic time. In the deepest sense, we are not separate from this cosmic evolution, but participants in it. Our thoughts and dreams, our scientific discoveries and artistic creations represent the universe becoming conscious of itself. Through us, the cosmos examines its own structure, ponders its own origins, and contemplates its own future. Whether we live in a bustling cosmic metropolis or a quiet cosmic suburb, we remain part of the same magnificent story that began with the Big Bang and continues through the formation of the first stars, the assembly of galaxies, and the emergence of complexity and consciousness. The mystery of our cosmic location, void dwellers or not, will eventually be resolved through careful observation and analysis. But regardless of the answer, we can rest peacefully knowing that we are connected to something vast and beautiful, participants in a cosmic story that encompasses the largest structures we can observe and the smallest quantum fluctuations that started it all. As you drift toward sleep tonight, you might imagine yourself floating gently through the cosmic web, surrounded by the vast architecture of space and time. Whether nestled in a cosmic void or embedded in the universe's denser regions, you remain a cherished part of the cosmos, a brief but brilliant arrangement of matter and energy that can contemplate its own existence and find wonder in the darkness between stars. The universe continues its ancient dance of expansion and structure formation around you, guided by forces both familiar and mysterious. Dark matter provides the invisible scaffolding for cosmic architecture. Dark energy drives the acceleration of space itself, and ordinary matter, the stuff of stars and planets and living beings, continues to create new patterns of complexity and beauty. As we near the end of our journey through the mysteries of cosmic voids and our potential residence within one of these vast, empty regions, it's worth pausing to consider the deeper philosophical implications of what we've discovered. The possibility that we live in a cosmic void raises profound questions about the nature of existence, the meaning of emptiness, and our place in a universe that is far stranger and more magnificent than our ancestors could have imagined. Throughout human history, emptiness has been viewed with a mixture of fear and fascination. Ancient cultures often populated empty spaces with spirits and demons, unable to conceive of truly vacant regions. The phrase "nature abhors a vacuum" reflects a deep-seated human intuition that emptiness should be filled, that absence is somehow unnatural or wrong. But modern cosmology has revealed that emptiness is not only natural, but dominant. The universe is far more empty than full, with vast regions of space containing virtually nothing but the faint echo of ancient light and the invisible threads of dark matter. In this context, the dense concentrations of matter that form stars, planets, and living beings are the true anomalies, rare and precious oases of complexity in an ocean of cosmic void. This realization fundamentally changes how we might think about our place in the universe. Rather than being inhabitants of a cosmos teeming with matter and energy, we find ourselves as residents of a universe where emptiness reigns supreme. The very fact that complex structures like galaxies, stars, and planets can exist at all becomes not a given, but a remarkable achievement against the cosmic tendency toward emptiness and dispersion. If we do live within a cosmic void, this perspective becomes even more poignant. We would be among the universe's most isolated witnesses, residents of one of its emptiest regions, observers of cosmic structure from within a vast bubble of near-nothingness. Yet somehow, despite this profound isolation, matter has managed to organize itself into structures complex enough to contemplate their own existence. This raises deep questions about the relationship between consciousness and cosmos. In a universe dominated by emptiness, the emergence of conscious observers capable of understanding and appreciating cosmic structure becomes an even more remarkable phenomenon. We are not just rare in terms of our cosmic location, but potentially rare in our very existence as conscious beings capable of contemplating the universe around us. The philosophical tradition has long grappled with concepts of emptiness and void. Buddhist philosophy, in particular, has explored the idea that emptiness is not merely absence, but a fundamental characteristic of reality itself. In this view, the apparent solidity and permanence of objects is illusory, and understanding the underlying emptiness of all phenomena is a path to deeper wisdom. Modern cosmology seems to echo some of these ancient insights. The cosmic web of matter that appears so substantial is actually mostly empty space. Even the atoms that make up our bodies are predominantly empty, with tiny nuclei surrounded by clouds of electrons occupying volumes vastly larger than the particles themselves. At every scale, from the quantum to the cosmic, emptiness appears to be more fundamental than fullness. If we live in a cosmic void, we are embodying this principle on the grandest possible scale. We are inhabitants of cosmic emptiness who have somehow managed to create meaning, beauty, and understanding within that emptiness. We are proof that even in the universe's most vacant regions, the potential for complexity, consciousness, and wonder can still manifest. This perspective also raises questions about our responsibilities as cosmic observers. If conscious beings are indeed rare in the universe, and if those situated within cosmic voids are rarer still, then we might have a special obligation to observe, understand, and appreciate the cosmic structure around us. We might be among the universe's few witnesses to its own architecture, and our observations and discoveries take on a significance beyond their immediate scientific value. The study of cosmic voids also reveals something profound about the nature of scientific discovery itself. Many of the most important insights in cosmology have come from studying not what's there, but what's missing. The discovery of dark matter came from observing the gravitational effects of invisible mass. The detection of dark energy emerged from studying the unexpected acceleration of cosmic expansion. The cosmic void hypothesis itself is based on trying to explain discrepancies between what we observe and what we expect. This suggests that emptiness and absence are not merely voids to be filled with knowledge, but are themselves sources of information about the universe. The cosmic voids that might surround us are not empty in any meaningful sense. They are full of information about cosmic structure, dark matter, dark energy, and the fundamental processes that shape the universe on its largest scales. In this vast cosmic context, sleep itself becomes a form of cosmic meditation, a daily return to the quiet darkness from which consciousness emerges. As your thoughts grow peaceful and your breathing slows, you join the gentle rhythms that govern everything from quantum fields to cosmic expansion. Rest well, fellow cosmic voyager, secure in the knowledge that you are exactly where you belong in this beautiful, mysterious universe. Whether in a cosmic void or cosmic fullness, you are home among the stars. Sweet dreams drift through the cosmic web, carrying you gently into the peaceful darkness where new wonders await discovery, and where the ancient light of distant galaxies continues its journey across the vast, welcoming emptiness of space.